Now we need to consider in some more detail the impact of power consumption. So before we go into a discussion of power consumption, let's consider the transfer characteristics of an Nmos transistor, just to fix some point. So we need to plot the current ID as a function of the gate to source voltage for a constant drain to source voltage. So as you know, the transfer characteristics is the following one, has the following behavior. So these are transfer characteristics. So the behavior is the following. Up to a certain point, the current is 0. So if this is VTN, for VGS smaller than VTN, the current is 0. And above, it goes up parabolically for long transistor with the behavior that we know. ED is equal to Kn times VGS minus VTN to the power of 2. So this is the saturation condition, and this is the off state. Okay. In the case of short transistor, as we discussed, we do not have a power of 2, we have a linear relationship, but apart from that, the situation is similar. Okay, the important thing to consider is that this is actually an approximation. Okay, it is not true that the current goes abruptly to 0 when the gate to source voltage goes below the threshold voltage. Okay, this is a strong approximation and comes from the fact that we simply say, okay, when the gate to source voltage reaches VTN, we have a channel. Before, when the VGS is smaller than the threshold voltage, we do not have any channel. But of course, the channel builds gradually, and therefore, discussing in terms of below threshold and above threshold as something that changes abruptly is a strong approximation. What happens is a slightly different thing, and let me write an expression which is much closer to the real one. It is something like this. We have ED also this is not exactly correct, but it's much more much closer to the correct one. 2 Kn times Vt to the power of 2 times the logarithm of 1 plus exponential of VGS minus VTN over 2 Vt to the power of 2. Okay. This is much closer to the initial one, and it is continuous. So this is valid also below threshold. Okay. So Vt is what is called the thermal voltage, which is Kt over Q, where K is the Boltzmann constant, T is the absolute temperature, and Q is the electron charge, the elementary charge. So this is a voltage. It is something that is equal to 26 millivolt at room temperature. So you should see here that when VGS minus VTN over 2 phi t is much larger than 1, the exponential dominates with respect to 1, so we can discard 1 here. Therefore, we have a logarithm of an exponential, which gives us the let's say, argument of the exponential, and therefore we have this expression that is written here in red. Okay, so we can simply derive the expression written here in red if we assume that the argument of the exponential, so VGS minus VTN, is much larger than 2 phi t. Okay, so we go here, back here, if VGS minus VTN is much larger than phi t, or 2 phi t. If it's much larger than 1, is the 1 phi t is also much larger than 2 phi t. Okay, so this is a particular case. If I remember correctly, actually here there is an error, because this works exactly if we put a 4 here. Okay, yeah, but it's a constant quantity, it's not that important. But you can see the limit, it's pretty easy. Now, the interesting thing occurs if that is not true. If VGS minus VTN, which is called overdrive, as we have already mentioned, is smaller than phi t, is not much larger than phi t. Because, of course, this is not true. This does not go to 0, let's say, abruptly. What is easy to understand is what happens in the other limit, because we can make some simplification. If VGS minus VTN is much smaller than phi t, what happens is the following. The exponential is smaller. We have a logarithm of 1 plus a small thing, which is equal to the small thing. So logarithm of 1 plus x, if x is small, is approximately equal to x. So this means that the current is just proportional to this exponential. So this is what we obtain, a current which is proportional. For simplicity, I eliminate all the constant quantities to the exponential of VGS minus VTN over 2 phi t. Of course, this yeah. Now, so what does it mean? That when we reduce VGS, the current does not go to 0 abruptly, but it goes to 0 exponentially, okay? Which is not exactly the same. So if I plot the current and as a function of the VGS on a semi-log scale, so I plot the logarithm of the current as a function of VGS, what we obtain is a different thing, because what we have here is that the 0 is not exactly 0. If this is VTN, let's assume that this is VTN. So, when VGS is larger than VTN, if we plot the logarithm, we obtain something like this. If VGS is smaller than VTN, this situation is true, and the current is proportional to the exponent of the to E equal e to the power of the overdrive over 2 phi t. And so the logarithm of E is proportional to the overdrive. So on a semi-log scale, I see a linear behavior here. Okay? I don't see, let me reduce the slope so that I use less space. No, I don't want it to pass from 0. Okay. I see a linear behavior. So the logarithm, this means that the logarithm of I is proportional to VGS minus VT. Okay? So this is where the line comes from. Okay, why I am writing these expressions and drawing these plots? Simply because if these transfer characteristics are corresponding to VDS equal to VDD, then this quantity that we have when VGS is equal to 0 corresponds to something that we call off current. So I off, by definition. So the off current is the current that we have in the transistor, in the Nmos transistor, when VGS is equal to 0 and VDS is equal to VDD. If you remember, is the current in the Nmos when the Nmos should be open, should be an open circuit. When, for example, when the output of the inverter is high, we have that the Nmos has a drain to source voltage which is equal to VDD and a gate to source voltage that is equal to 0. Okay? So, and this is an important quantity because the power consumption in static condition is going to be proportional to the off current. So, for the moment, look at this definition and let us consider again the inverter. So, this is the inverter again. This is V in. And this is V out. Let's assume that V in is equal to 0. And then V out is equal to VDD. You see that in these conditions, this is the gate, this is the source, and this is the drain. VGS is equal to 0, and VDS is equal to VDD. So we are exactly in the conditions that I've described before. The MOSFET, the inverter has a high output. This current is I off, by definition of I off. And of course, I off goes through the Nmos, but also goes through the PMOS, because the two are in series. Okay, so the power consumption is of this logic gate is let's say the supply voltage times the current that the supply generator has to provide, which is exactly I off. So the power consumption is called PS in this particular case and is equal to VDD times I off. Okay? So this is called static power consumption. Because it's the power consumption that we have when there is no switch of the logic gate. The logic gate is simply conserving the state. We have an input that is 0, the output is high, there's an off current that goes through the transistors, and the power consumption is proportional to the off current. So if you look at the expression that I've written above, look at this expression. The power consumption is proportional to this exponential, but VGS is equal to 0, so the power consumption is proportional to exp to minus VTN over 2 phi t. So this is, let me write not equal but proportional. I'm not interested in the constants that are not important here. I have an exp of minus VTN over 2 phi t. So this is a critical issue because and important factors are these two. The most important one is this one. The power consumption depends on the threshold voltage, and it depends a lot on the threshold voltage. It depends exponentially on the threshold voltage. So if we reduce the threshold voltage, the static power consumption increases exponentially. And this is exactly the reason why we cannot play too much with the threshold voltage, because we are increasing a lot the power consumption. Okay? And the other issue, which is of course important, is that the power consumption, the static power consumption, is also proportional to the supply voltage. Okay? But there's also an additional consideration, but I don't want to discuss it too much, but it's also dependent on the temperature, because the temperature appears in various points in the expression of the power consumption. So you could, in principle, look at also that dependence, but I'm not interested in that now. But remember, we cannot play too much with the power consumption, and the power consumption is proportional to the supply voltage. Okay. Now, of course, historically, that is not the most important component of power consumption of a digital circuit. The most important component of the power consumption is what is called dynamic power consumption, which is the power consumption that you have when the logic gates switch. Okay? This is a point which is important from the historical point of view, because I mean, until the late 70s, the main technology for digital circuits was not Cmos technology. It was a technology that was called TTL, and it was essentially based on bipolar transistors until the late 70s. Okay? And the reason why it was more used was essentially because it was much faster than Cmos. So it was much faster. But had a significant static power consumption. So when the performance of both bipolar and Cmos increased a lot, then power consumption became a significant concern, and only at that time the Cmos became important. Because with Cmos one could say, okay, there is a negligible power consumption in static conditions, because as you know, in the inverter when the output voltage is constant, one of the two transistors is off. So with good approximation, the off current can be considered 0, and therefore, at least with CMOS, you can cut completely off the static power consumption. So from a point of view of industrial introduction of the technology in the market, this was the most important selling point. Okay? Now, at that time, CMOS was still less performing than bipolar, but this huge advantage was the reason why it was introduced. And then what happened is that, of course, the performance increased because, for the reasons we have discussed from a quantitative point of view today, because the channel length could be reduced, and therefore with reducing the channel length, one could increase the clock frequency. So, and the performance could increase. But the main reason was for the introduction of CMOS was the fact that CMOS had a very small, almost negligible static power consumption. Okay, I'm insisting on this point because this was true in the late 70s, was true in the 80s, in the 90s, at the beginning of the 2000s. It started not to be true anymore, because of a simple reason that what happened is that the supply voltage was reduced with the reduction of the size of the transistors, and also the threshold voltage was reduced, because when you reduce the supply voltage, you need to reduce also the threshold voltage a bit. Otherwise, you cannot, let's say, switch on fully the transistors. But you see the behavior. The static power consumption is exponentially dependent on the threshold voltage. So what happened is that the threshold voltage has been reduced up to a point in which you cannot discard anymore the static power consumption. And indeed, if you consider a modern microprocessor, modern means a microprocessor of the last 10 years, because this ratio has not changed that much, more than half of the power consumption is static power consumption. Okay? So, because this has become a really an important component. Okay? And the reason why the reduction of the threshold voltage has virtually stopped, technology after technology, is exactly the fact which is, let's say, expressed by this formula, that if we reduce a little bit more the threshold voltage, we increase too much the static power consumption. Okay, so basically we cannot reduce the threshold voltage anymore. Okay, and I will show you some, let's say, I have some plots of these quantities as a function of time in commercial microprocessors, and you can see the difference. Basically, the VTN cannot be decreased anymore. Okay, it's already too much, the static power consumption. Now, let's consider a bit the dynamic power consumption. That is a quantity that you should already know, but I need to very quickly recall the basic things. So the dynamic power consumption is the power consumption that we have when the logic gate switches. So let's look at it. Okay, again, let's consider a simple inverter. And the load, the capacitive load. Okay, and let's consider just a cycle of the input and the output voltage. So let's assume for example that the input voltage is initially high, then it goes low, then again it goes high, and so on. And let's just consider a simple cycle, just a period. So the output voltage as you know does the following thing. When the input is high, the output is low. Then after a switch that we have some delay, and then the output voltage switches to a high, and then again it switches to low. Okay, this is something that we have already studied. Okay, now what is the power consumption in during this switching? For example, here, from here to here, we have the switching. So before we have static power consumption, then again the input and the output do not change, so we have static power consumption up to this point, because here the inputs start to change, and then we have another switch, and then it is static again. So we have dynamic power consumption here and dynamic power consumption here, only during the switches. Now, the easy thing is not to consider the power consumption instant by instant, but to consider the total energy dissipated for the switching during a period, so that we have an idea of the average dynamic power consumption. So let's look at the energy dissipated by the power supply. In a period. Instead of period, let's write cycle. Okay, this is pretty easy to compute, because in a cycle what we have is, first we have to charge the capacitance. So let's call this phase A. We need to charge the capacitance. During A, the Pmos is conducting, the Nmos is not conducting, and therefore we have to put some charge from the supply voltage to the capacitor. Okay? This is what happens during the A phase. Then everything stops, and then we have the B phase, and during the B phase the output voltage goes down. Of course, in order to have the output voltage go down, the Nmos has to be on and the Pmos has to be off. So during the B phase, current goes in this direction. So if you consider the supply voltage generator, the battery, it has to provide the charge during A, and then during B it only collects the charge at the other electrode. Okay, that's it. So if we want to compute the energy, we just need to integrate the instant power consumption. We have to do the following thing. The energy is the integral of the instant power, VDD times I, and I is the current provided by the supply voltage in dt. This is, by definition, the energy. Of course, here, this is easy to compute because VDD is constant, so I can take VDD out of the integral, and then I have just an integral of the current in time, and of course the integral in time of a current is a charge, okay? And what charge is that? Is the charge that I have to put on the output capacitor. But it is easy to know because this charge is since the output capacitor has a capacitance C tot and has to go to a voltage VDD, the charge is C times VDD. So we have VDD times this, which is C tot times VDD. So the energy consumed per each cycle is C tot times VDD squared. Okay? And this is the total energy dynamically dissipated. So if we want the let's assume that we have a cycle every clock phase. So you can simply assume that the average power consumption, dynamic power consumption, is the energy dissipated in a cycle divided by the time duration of a cycle. Okay? So the dynamic power consumption can be written in this way: P dynamic is equal to the energy divided by T clock, which is C tot times VDD squared, and the inverse of T clock is F clock. Okay? This, of course, is true if there is a switch cycle every clock period. Typically what one writes is that one typically defines a sort of activity factor which takes into account on average how many switches you have for every clock cycle. So typically it's never true that the logic gate switches at every clock cycle. Only the clock switches at every clock cycle. The rest switches at very lower rates. So one typically uses now a quantity which is called activity factor, and is a number between 0 and 1, which says, okay, what is the fraction of clock cycle during which you actually have a switch? Okay, so this is called activity factor, and it only in typical logic circuits is a few percent, so 7–8%, no more than that. Okay, activity factor. Now, okay, so you should consider these two important parts. This part, the dependence over the supply voltage to the power of 2, and the linear dependence on the clock phase. And also this is important, the dependence on the activity factor. So if you don't let all your blocks, your digital block to switch every time, you can save energy. Okay? Over the whole chip, it is easy to make the calculation because you see this is true for one logic gate. If you sum up over all the logic gates in the same chip, for example in the same microprocessor, you see that all the quantities are the same. You only have to sum all the capacitances of all the logic gates. So that is relatively easy to do. So we have PD is equal to a sum on all the logic chips of all the capacitors times VDD times F clock times an average activity factor for the whole chip. So you have basically the chip capacitance times VDD square times F clock times alpha. Okay? Now, this is the average dynamic power consumption. We have already computed the average static power consumption, because for the whole chip, what you have is VDD plus a sum of the off currents on all the logic gates. So basically here you have VDD times I off, let's say, chip, for the whole chip. And then when you have both, the total power consumption is equal to the sum of PD plus PS. Okay. So, now let's discuss a bit these quantities. So it should be clear up to now that there's a strong reason for reducing the supply voltage as much as possible. Okay, because if we reduce the supply voltage, we can reduce both VDD, both the dynamic power consumption and the static power consumption. Okay, so there is this trade-off in the technology generations in order to reduce VDD, because we know that if we reduce VDD, we reduce the power consumption, but at the same time, we lose in performance. Okay, you remember what we discussed before. So we need to reduce VDD because power consumption is important. Of course, we lose in performance, and then we have to gain in performance by improving something else. And so historically, the way in which we have compensated this reduction in performance due to the reduction of VDD has been by reducing L. Okay, mainly by reducing L, we have increased the performance more than the reduction in performance that was given by the reduction of VDD. So the scaling, the reduction of the size of the transistor has been extremely important, because it has been the only thing that has allowed to improve the performance while at the same time reducing the power consumption. Okay? It's not the only thing. There are different things that can be done. For example, I mentioned before the mobility increase. You see that mobility has no effect on the power consumption, but it can improve the performance because it can reduce the propagation delay. And so, let's say, historically, at some point, the only way to improve performance was to increase the mobility, and therefore, it has been done. Okay? And it's not something you can, let's say, then change. When you have done this increase in mobility, you have to keep this deformation, this strain on the silicon in the channel, because otherwise you cannot know, you don't know how to, let's say, improve performance in other ways. But if you look at these two expressions, the expressions for the power consumptions and the expressions for the propagation delay, you can explain most of what has changed in the various technology generations in the last years. Okay? Now, I would like to spend some time on the scaling of Cmos technology and exactly what happened. So you know why it is important, but let's look at it in detail. So okay, let me just change page. So the important quantities are the following: PD, is equal to C chip times VDD square times F clock times alpha. PS, the static power consumption, is VDD times I off, and the propagation delay is C VDD over 2I on. Then for long transistor is C VDD over 2K VG. These are expressions that I'm just copying here for convenience. Okay, and for short transistors, it's a bit different because I have just a power of 1 here. Okay, so here we have 2 VSAT. Okay. Then the other quantities that are important to consider is that T clock is something like, let's say, 100 TP. Okay, now let's use these formulas to look at the scaling. We can consider two different types of scaling factors. We have a scaling factor for voltage, let's call it lambda. And let's assume that the scaling is larger than 1. So L lambda equal to 2 means that we divided by 2 all the voltages. Okay? And then we can assume a different scaling factor for geometry, which we call S. Okay. So let's consider the different quantities. And the different scaling factors. Okay. So, first, geometry. W, L, and Tox are the geometrical quantities. They scale like S. Okay, just by definition, the scaling factor for geometry is S. Okay. Then the voltages are VDD and VT and VTP. Let's assume that they scale by lambda. Okay? Okay, with this assumption, what is the scaling of TP? You should consider two different situations. The situation for long transistors and the situation for short transistors. Because in various stages of the technology, the transistors have been long in the first years and short in the latest years. So, what happens here? For the long transistors, you see that there is a lambda if the voltages are scaled by lambda, then the tau p goes like 1 1 over lambda, because you have the power of 2 in the voltages in the denominator. So it is 1 over lambda for the long. Let me separate the two things. Long, it is 1 over lambda. And for the geometry part, which is included here, we have already discussed it, because C is proportional to W, L, and Tox at the denominator, and K is proportional to W over L and Tox. So you see that W and Tox are not important. L is to the power of 2, because it is in the numerator, it is in the denominator, but as 1 over L. So it is proportional to L square, and therefore we have an S square here. S square over lambda. For the short transistors, the situation is a bit different, because lambda is not important, because we have VDD to the power of 1 at the numerator and also at the denominator, so they do not scale with lambda. Vsat is a constant, is independent of every geometrical consideration, and C is proportional to W, L, and Tox. If the three of them scale as S, we have S times S over S, which says that C and therefore also TP scale as S. So they scale as S. So we have two different types of scaling, S square over lambda for the long ones and S for the short ones. In general, in general we are considering S different from alpha, but this is not necessary. Okay, with TP is also T clock, because TP is proportional to T clock, and therefore the clock frequency, which is inversely proportional to T clock, scales as the inverse of T clock, of course. So F clock, which is an important parameter because computational performances are proportional to F clock, says us that for long transistor this goes as lambda over S squared, and for short transistors it goes like 1 over S. Okay. Then the power consumption. Let's consider only the dynamic power consumption, okay, which is actually, which has been for some time the most important factor. The static power consumption, okay, you see, in the case of, we have to distinguish between long and short. In the case of long, what we have is the following thing. Let's consider for one logic gate. Okay, so for one logic gate we have this expression. So the C part goes like S. VDD goes like lambda squared. So we have C S times lambda squared times lambda over S squared. So this goes like lambda to the power of 3 over S for long transistors. Okay? For short ones, we have S times lambda squared times 1 over S. So we have only lambda squared. Okay, so this is the power consumption of a single logic gate. the area occupied by a logic gate, of course, is proportional to W and L. So it goes in all cases like S squared. Okay, of course, these are approximate expressions. Now, if we consider PD over area, cioè the area, the power consumption per unit area, in the long case is equal to lambda to the power of 3 over S to the power of 3, and in the short case is equal to lambda to the power of 2 over S to the power of 2. So these are the normal scaling rules. Okay, the only thing that we have not considered here is that the power consumption is not only the dynamic power consumption. There is also the static power consumption, which can be important. Okay. Now, why I am mentioning these quantities? Because from the historical point of view, things have changed in the sense that there have been 3 different phases for the scaling and 3 different types of evolution in the case of Cmos processors. And okay, of course, I am old enough to remember them, but I think they're important to be understood, because I mean, if we know how things have evolved and why, we can also try to understand what is going to happen in the near future. And of course, what happened had an impact on also the type of use of the microprocessors and the type of applications one could run on the microprocessors. So let's discuss the details. So the 3 phases have been the following. First phase, phase 1, essentially since the introduction in large quantities of Cmos processors up to, let's say, 92, okay, from the 80 to 92, so 1980 to 1992, the evolution has been the following. Basically, as I mentioned, before 1980, most of the Cmos logic was, most of the digital logic circuits were done with TTL logic. And gradually, there has been a change from TTL logic to Cmos logic. But the most important aspect in those times was to maintain compatibility with TTL logic. So TTL logic had supply voltage of 5 volts, and also Cmos logic for several years maintained the 5-volt supply voltage. So there was this so-called constant voltage scaling. The voltages were kept constant. Essentially, the supply voltage of 5 volts and the threshold voltage close to 2 volts, depending on the technology. And gradually, the size of transistors were reduced. So we had a lambda equal to 1, constant voltage scaling. So lambda is equal to 1, which means that VDD is kept at 5 volts, and S is larger than 1. There was a scaling only of the geometrical dimensions. Okay? What is the effect of this scaling? You should look at these quantities. Of course, you can increase the clock frequency a lot. Okay? Because if lambda is equal to 1, and I should check the, let me just check the quantities. No, probably I should check this again, because probably I mixed the numerator with the denominator. Let me check. When I wrote TP, for long, okay. Okay. Oh, okay. There is an okay. You can describe it simply here. So, okay, what I did here, it's something that is not, let's say, according to the convention that I decided at the beginning. Because you have seen, I wrote these scaling factors, and then I substituted the scaling factors to all the quantities, which means that the quantities are proportional to the scaling factors. I wrote at the beginning something different, that I said at the beginning that if the voltage scaling factor was 2, it meant that the voltage has to be divided by 2. Okay. Instead, I let's say computed the different values considering the opposite thing. Okay. So the simplest thing we can do here is to change this quantity. Okay, so that everything is correct in the table. So if the voltage scaling is 1/2, it means that the voltage has been divided by 2. So it has been multiplied by 1/2. So in this way it works. Yeah, I don't know why I continue the reason like that. Okay, with this variation, everything is correct. I just assume it differently. Okay, this implies that if you look at the lecture of last year, all the scaling factors are reversed. Okay, just because I use the opposite convention. Okay, I have done it, so let's keep it this way today. Okay, now, what happens here? Look at this situation. If we have a constant lambda, and only we vary the dimension, what happens here is that the propagation delay goes down, because lambda is equal to 1, and s is smaller than 1, goes down faster for long transistors, and goes down slowly for short transistors. Okay, but in any case it goes down. This means that the clock frequency goes up in the same way. Just if you focus on short transistors, because the formulas are simpler, you see that if I divide by 2 every length, I can increase by a factor of 2 the clock frequency. Okay, and that is of course an advantage. The power consumption does not change. The area goes down, and therefore the power consumption per unit area goes up, and goes up a lot, because it goes up like 1 over s squared. So with the square of the reduction I can do on the geometry. Okay, so this is what we have. We have an increasing clock frequency as a final, let's say, behavior. Strong increase in clock frequency. Strong increase in f clock, and here I should write smaller than 1, okay? Because it goes like 1 over S in short transistors, and increase in power consumption per unit area, because that is proportional to 1 over S squared, okay? The power consumption per unit area goes up to 1 over S squared. Okay, this is a problem. Okay. Because you see, the power consumption of a single logic gate does not increase that much. The power consumption, the area of a logic gate goes down quadratically, and therefore the power consumption per unit area goes up quadratically. Okay, this is easy. But what is the problem? Is that typically, if you scale down the dimension of a single transistor, what you want to do is to increase the number of transistors per chip. So the total area does not decrease even if you decrease the size of a single transistor, because you increase at the same time the numbers of transistors you have per chip. So what happens in practice is that the area of the chip does not decrease in any case, and you have a power dissipation which is increasing a lot. Okay, so you have much better performance, but at the same time you have a strong increase in the consumption, in the power consumption of the whole chip. And this is, of course, a problem. The second problem that you have is a reliability problem, because you have the same voltages applied to smaller and smaller transistors, and therefore these transistors sometimes have a breakdown because you're stressing them too much. You're applying too large electric fields. Okay, so problem. There are two orders of problem. There are two orders of problem. One is total power consumption, which is too high. And reliability, because the electric field is too high. The electric field is proportional to the voltage over the length, and therefore if you keep the voltage constant and you decrease the length, the electric field goes very high. Okay, so, and during this period, basically the length of the channel went from something like let's say 10 micron to 0.25 micron. So there was a decrease in the length of a factor of 40. This S was equal to 1 over 40. Okay? So you can imagine the increase in power consumption. The second phase has been more or less from 1992 to 2002, other 10 years, maybe a little bit more than 10 years, and was a phase of constant field scaling. Constant field scaling means that lambda was kept equal to S, and of course both smaller than 1. Okay. In practice, what you have is that if you scale the voltages in the same way as you scale the length, then the electric field remains more or less constant. And indeed, this is the reason why it is called constant field scaling. Okay, so you stop the reliability problem because of too high electric field. You can keep that part under control. You are scaling the supply voltage. Of course, you lose compatibility with TTL, but at that time it was not important anymore because TTL were dead since a long time. But what happens to the various quantities? The important part that you should see here is that you can still increase the clock frequency because for short transistor, for example, the clock frequency goes like 1 over S. So you can still keep to increase the clock frequency, but you decrease the power consumption of a single logic gate, and the power consumption per unit area, since you decrease the power consumption of the logic gate in the same way as you decrease the area of the logic gate, the power consumption per unit area remains constant. Okay? So you could keep the same power consumption per unit area while increasing the clock frequency, while increasing performance. So this was basically the golden age, because year after year there was a record clock frequency for the microprocessors and no significant problems in terms of power consumption. Because of course the actual power consumption of the chip increased a bit, but only because the chip became larger and larger in terms of area. But the power consumption per unit area actually was constant. So this was actually the easy way, the easy evolution of CMOS technology, and it was basically for 10 years. Okay, so we have increase of clock frequency proportional to 1 over S and constant power consumption per unit area. Basically, let me show you some numbers from 92 to 2002. VDD went from 5 down to 1.5 volt in 10 years, so a factor of more than 3. L, actually, I was wrong, I mentioned 0.25. Actually, 1992 was 0.5 micron and went down to 0.13 micron. So more or less the same factor, a little bit larger than 3. Not exactly the same factor, but very close. And TOX, the oxide thickness, went from 7 nanometers to 2 nanometers. You see exactly the, more or less the same type of scaling. And the threshold voltage went from 1.5 volt down to 0.4 volts. Okay? So this occurred in the this was the situation at the start of the century in 2002, more or less. So then at some point things started to change because there were some problems. I mean, it was not possible to continue this situation for a few reasons. Let me mention just a couple of them, the two most important ones. And one is this one. Okay? Because you see the oxide thickness was from 7 nanometers to 2 nanometers. It's very thin. You start to have gate leakage. So you cannot discard anymore the current that crosses the insulator and goes to the gate. So this was one problem. And the second problem was that this was too small. So static power consumption increases. You remember, the static power consumption depends exponentially on minus VTN. So until this point, you can discard the static power consumption, but then you cannot decrease this part anymore. Okay? And this is the problem. So this is the reason why basically the oxide, the type of oxide for the gate dielectric was changed from silicon on insulator to other material, from silicon oxide to other materials, because the other materials had a higher dielectric constant and then could allow a thicker thickness of the oxide, and therefore one could reduce the problem of gate leakage. And actually the static power consumption was indeed a real problem, because what happened at that point? Okay, let's say the industry could not reduce the static power consumption below this. It could not decrease the threshold voltage below that number. Otherwise, the static power consumption would be under control, and therefore had to stop the decrease of the voltages. So we entered a third phase in which there was no voltage scaling anymore. Voltage scaling was almost stopped, and it was possible only to continue for only some time, for a few years, with geometry scaling. Okay, so let me summarize this part. Phase 3, voltage scaling is stopped. Geometry scaling continues. What do you do? If voltage scaling stops and geometric scaling continues, there is a real problem. You remember, the power density per unit area goes up. And actually, the only way to reduce to stop this increase of power density per unit area was to stop the increase of frequency. So, no increase of f clock. So you should put attention here. You continue to decrease the geometry, which in principle would decrease the propagation delay, so would allow you to go faster, but instead you don't go faster. And you don't go fast, you do not increase the f clock, because otherwise the power dissipation per unit area goes absolutely out of control. Okay? So what happens here? Let's look at this at the table we have drawn here. So you see lambda is equal to 1, you have s smaller than 1, so in principle you could increase the clock frequency, but you don't do that. Okay? So if you do not increase the clock frequency, and you look here, what happens is the following. You do not increase the clock frequency. You can do the following thing. This is for the same yeah, this is more or less, if you consider just a single logic gate, this is proportional to W over to W L over Tox, so they go like S, so you have S squared over S, so this goes by like S. See, so you have PD, which is proportional to S, and the area goes down like S squared. So you have basically PD is proportional to S, to the geometrical scaling. The area is proportional to S squared, and therefore PD over the area is proportional to 1 over S. So you have a slight increase, of power density per unit area, which is not good. It was not like 1 over S squared, but it's still too much per unit area. So you do something else. You change a bit things and you say, okay, I don't simply stop voltage scaling, but do the following thing. I slow down voltage scaling, and if voltage scaling is slowed down, so it's almost stopped, not really stopped, then and if F clock is reduced, instead of keeping it constant, I reduce F clock. Is a bit more aggressive as a solution. Then I can keep PD over A more or less constant. Okay, so and this is actually what happened from the historical point of view. First, people started to stop voltage scaling and to stop the F clock, but so it was not enough. They could do it just for a couple of years. Then they started to decrease the clock frequency and to decrease very, very slowly the supply voltage in order to reduce this number and to keep it constant. And this is what happened. What is happening now? If you look at the let's say technical notes of the microprocessors that is used in notebook computers or in smartphones, actually the clock frequencies are decreasing. Voltage is still scaling down, but very, very slowly. Now the typical voltage applied to a processor is 1.1 volt. Okay, from 1.5 in 2002 to 1.1 now, it means that it is almost constant. And still, it is good enough because you can increase the performance not by increasing the clock frequency, by increasing the numbers of parallel cores that you have in the microprocessors. So the way has been just to go in a direction of saying, okay, I can reduce the size of the transistors. In the same area, I can put much more transistors. They do not go faster because I cannot allow them to go faster because of power consumption, but I can use them in parallel, and therefore in this way increase the total computational power of the microprocessor. And so this is the reason why from 2005 there has been no increase on clock frequency, but a complete switch to double core, quad core, 8 core, and so on. And this is the situation in which we are now. I just wanted to show you a historical plot of the situation that tells you what's been happening. And no, let me just, there's a plot that I think is interesting. So, okay, let me show you these two. Okay, so this quote is just as an illustration of the points that I mentioned. First one, for Intel microprocessors, this is the active power consumption, which is the dynamic power consumption, and the leakage power consumption, which is the static power consumption. So active means dynamic power, and leakage means static power consumption. So as I mentioned before, in the 80s, you could discard the leakage. Then at some point, it started to matter a lot, and because you are decreasing the threshold voltages, and therefore you are increasing a lot the static power consumption. And you can see that it's becoming important here. In 2001, 2002, the two becomes comparable. And if you do not do anything, if you do not change the type of scaling, the leakage power consumption becomes absolutely dominant, and it ruins everything. So at that point, at the beginning of the century, it was absolutely necessary to stop the scaling down of voltages. And this is what this has been a huge change in the industry, because this scaling meant the introduction of multi-cores, basically. This is the power density. Also, this I think it's important. It was a talk by a VP of engineering of Intel in 2001. Basically, it was the most important conference in the field of, let's say, Cmos technology. And he basically showed this plot. This is the power density, so power consumption per unit area as a function of time for different generations of Intel processors. And so he mentioned the following thing. He said, okay, from the 70s to the 80s, basically we observed an increase, but just because the technology was starting, actually. Then we had an almost constant power consumption per unit area. Then we are starting to see an increase. And this increase actually was due to this. The first increase was due to the fact that the static power consumption became important, like here. Then at some point, they stopped the decrease of voltage. They stopped the voltage scaling. And so if you do not stop the clock frequency, you observe a steep increase on power consumption. And then it showed, okay, this is the power density. It's going to increase in this way. A nuclear reactor is here, a rocket nozzle is here, and the sun surface is almost here. So in a few years, we will have a power density which is absolutely out of control. Okay, and so I mean, this actually triggered the action of completely stopping, reducing instead the clock frequency, and trying to go towards a multi-scale processors. And indeed, this is what happened. This is the power consumption for a complete microprocessor, not the power consumption per unit area, as a function of the time it was introduced in the market. So you see that the increase is slow but significant, and it is basically due to the fact that the area of the chip is increasing during these decades, and that at some point you stop, because essentially you cannot, when you reach 100 watt per a single microprocessor, this is for a desktop computer, of course, this stops. And the reason why it stops is that actually you increase the number of cores and you reduce the frequency. So, and now actually we are here and also decreasing because mobile processors have become more and more important and they need to consume less than 10 watts of power. So the evolution has changed a lot, and now we are basically in the range in which we prefer to reduce the performance and to keep the power consumption as small as possible. So the last, and of course this is an example, is a very simple example, but I think it's useful to just to close this lecture. And basically this is not a new Intel chip for Intel processor for data centers actually, and of course this is a 4-core. If you this is the let's say the photograph of the chip, you can see you have 4 cores. They are basically identical, and they run typically at a clock frequency which is 2.5, 2.7 gigahertz. So pretty below the record of 3.5, 3.7 of the early 2000s. Okay, and yeah, the core are identical. The caches are pretty large, and typically now in modern processors, more modern processors, the situation is pretty much similar. You have 4, 6 cores, 8 cores, and a very large cache between them. In more modern microprocessors, for example, I already mentioned it in the A11 from Apple, in the new Apple iPhone, there are heterogeneous cores. So there are high performance cores, and there are also low power cores. Depending on the application, use one or the other. And this is something that has been introduced 2 years ago, not before that. Before 2 years ago, in multi-core processors, you had identical cores. Now, heterogeneous cores are emerging, especially for mobile applications. Okay, we stop here.
For the time.